uh, excuse me one sec. These are all approximately 211 as of today. The pandemic has changed things a little bit, made some things a little bit more costly, but again, very inexpensive sensors that can be used to measure these chemicals. So briefly, real quick, some of the sections we're going to go over. We're going to introduce VOCs and E-noses, then discuss data acquisition, so that's our hardware and experimental process, and then data processing software, and then finally, we'll see chemical prediction and the results. So again, introduce VOCs. What are they and why are they worth studying? So VOCs, volatile organic compounds, are present in natural and artificial materials. They're a natural marker in biological processes such as growth, decay, or stress. And they're also reactive chemicals that are prone to evaporation and have a low boiling point. VOCs are also a part of human pollution produced from like car emissions, refinement, industrial procedures, things such as production of plastics, rubber, various other processes, and are capable of existing in the atmosphere for long periods of time, upwards of several months, and they're detrimental to human health. So more ways that they affect the human body. They're capable of entering the body through different membranes, primarily through the skin, as that's our largest organ. And other ways they affect the human body, headaches, allergies, exacerbation of other symptoms, and also other long-term ailments. Excuse me. VOCs are also a byproduct of biological processes, metabolites that are released from the human body due to other things that could be interacting inside of the human body. They can indicate things such as bacterial infection, have been used to diagnose cancer, and also can indicate metabolic disorders, specifically things such as like diabetes or ketosis inside the body through emissions of ketones inside the breath, and also indicate stress. Plants utilize VOCs as well. They can use them as a way of communication, a way to indicate damage to plant structure, pests cause damage, and that can indicate specific types of damage to the structure of a plant. And pollutant VOCs that we discussed earlier reduce the amount of carbon fixation during photosynthesis, so the amount of carbon that's pulled from the atmosphere. If I'm not mistaken, the mechanism isn't completely known, but it actually reduces the amount of carbon that plants, again, will fixate during the photosynthesis process, excuse me, and also plays a role in oxidation of our Earth's atmosphere, exacerbating the climate change. So going further into E-noses and why an E-nose system was selected here. So electronic noses, there's several technologies that are used to analyze VOCs, again, volatile organic compounds. Gas chromatography, mass spectroscopy, and nuclear magnetic resonance spectroscopy are two methods that are used in clinical settings for diagnosis. And then E-noses, there's a gradual shift in clinical settings, again, for more non-invasive methods of diagnosis. But the other two spectroscopy methods require more highly trained operators, are much more costly, and require more time to produce results, yet they do provide much more selective analysis of the chemicals that are present. E-noses are much more cost effective, generally are more portable, require much less training, operator training rather, while still allowing the high throughput data analysis. These electronic noses have been described as a device to mimic mammal olfactory systems and recognize odors, and are almost always paired with recognition softwares. So E-noses specifically generally have chemical gas sensors, metal oxide, semiconductor sensors, and other sensors similar. These use a reactive detection layer. The different sensors are cross-reactive, again, between the different sensors, each responding differently to the VOCs or chemicals that are present. This E-nose, as you can see in the bottom right, we'll get more into, is the one that was developed for this work, paired with software, again, for pattern recognition. And we'll discuss the mechanism of these sensors later in this presentation. Again, metal oxide sensors, metal oxide MOS type gas sensors, excuse me, have broad sensitivity to different VOCs, but they lack the selectivity. So unlike our spectroscopy methods, these are unable to provide a specific makeup of an emission or a signal or a sample that's been collected. So the question again is, can the machine learning, excuse me, can machine learning be used with citizen science level e-nodes to build a machine learning model for which chemical labels can be predicted? And so to be specific, this work that's done, there's no breathing or sniffing or movement of air specifically for to move air across the sensors, and there's no temperature manipulation. Excuse me. Introducing hardware for the next section. So we're introducing the hardware components, how the MOS gas sensors function, and then I'll show some wiring diagrams and images of how this system is set up. So the hardware components that we're going to discuss real quick: Raspberry Pi, the MQ series of MOS sensors, a BME 680 environmental sensor, MCP 3008, a A to D converter, analog to digital converter, excuse me, some logic level converters, the Pi-T cobbler, and a power supply module. So the Raspberry Pi, some people may be familiar with this, is a single board computer, approximately the size of a credit card, fairly small, fairly portable. This system runs Raspbian, which is a form of Linux, has wireless internet capabilities, and has GPIO pins with which we use to interface with our instrument. So the MQ series MOS sensors, specifically MOS semiconductor type gas sensors, which all these sensors are, have broad sensitivity and low selectivity. Again, cannot identify selective chemicals inside of a sample. They produce a voltage signal, and similar sensors that most people may be familiar with are found in like smoke detectors or blood alcohol detectors, breathalyzer, I believe. And again, very low cost, typically $2 thereabouts. Could change depending on supply and demand. Currently, I know things are getting kind of crazy, or have been rather, but again, fairly low cost. So kind of specifically to show how this works, each one of these sensors is mounted to the backlight, I believe I pronounce it backlight base here, but this sensor, the sensing elements, excuse me, are inside of this anti-explosion network stainless steel mesh, which is specifically created to prevent any flammable gases from exploding, as a lot of these are used to measure explosive or flammable type gases. So that prevents from some sort of catastrophic failure. And it's held on by a clamp ring. And this specifically is the MQ5 sensor. So this next image here shows the anti-explosion network actually peeled back. And you can see the sensing element and then our 6 leads. So you have the 2 heating element, or the 2 leads there primarily for the heating element, as well as the 4 output leads. You can see that sensing element there is actually in aluminum oxide with a coating of, or doped, I believe is the correct word. It's a coating of tin oxide, tin 4 oxide, or SNO2, as I may refer to it in the future. So these MQ series MOS sensors measure resistive changes inside the sensor. The semiconductor is coated with the oxide, again, SNO2. Depending on other types of MOS type sensors, you may see different oxides. Again, these specifically are tin oxide. The heater maintains an operating temperature. These all operate, I believe, from 200 degrees Celsius up to 400 degrees Celsius. The oxide, the SNO2 oxide, the tin oxide, absorbs free oxygen in the air, and this reduces the electron flow and the signal goes down. So electrons are bound to the oxygen inside the SNO2. When a reducing gas, or the VOC rather, interacts with the sensing element, less oxygen is then in contact with the semiconductor, which frees up our electron movement and our signal goes back up. So this reaction is reversible and repeatable long term. And the MOS sensors, again, use tin oxide. MQ series gas sensors are mounted to the backlight base, like we discussed, and excuse me, each one of these has an LM393 comparator for digitizing our signals with a built-in potentiometer, which is used to dial in your digital output, which is not used in this work, but I'll still present it. Again, the potentiometer there is used to dial it up when you have a specific gas that you want to be sensitive to, a specific ppm amount rather, you can dial that in. And you see here our LM393 and the 4 leads that we use to interact with our solderless breadboard. The BME 680 is our environmental sensor. Measures temperature, humidity, and barometric pressure. It also contains its own MOS sensor. Again, these lack selectivity. This one is just a generalization. And you can see here a few environmental, the temperature and humidity readings that it can take. The ADD converter is used to add 8 channels of input, which our Raspberry Pi is incapable of from the factory. The analog readings are, the analog input is needed for our sensors. The logic level converter is used to convert to from our high 5-volt logic down to the 3-volt logic or 3.3 volt logic that the Raspberry Pi requires. Otherwise, you could damage your GPIO pins. We've had to use 2, as each one of these converts high to low, only 4 leads or 4 pins. And so for all 8 of our sensors, we needed 2 of these. Excuse me. The Adafruit T-cobbler is used to hook up to our solderless breadboard and allows us to wire to this T-cobbler and then through a 40-pin GPIO ribbon cable connect to our Raspberry Pi. We also have the HW131 power supply module, which is used to provide additional power to our sensors, as the Raspberry Pi is not capable of providing enough power to the sensors without this, and you'll get throttling issues or low voltage issues with your Raspberry Pi. So this makes sure everything runs efficiently and effectively. This right here is a fritzing wiring diagram. I'll show in just a moment the real world. It's not quite as pretty, the real world wiring of this, and you can see how everything, you can kind of trace everything back. We have our MOS sensors going to the logic level converters with our MCP 3008, and then that gets wired to the cobbler, which then again, the ribbon cable will jump over to the Raspberry Pi. You can also see here we have resistors. We use 10,000 ohm, 10K ohm resistors in this work. Those are used to constrain the voltage signal from our MQ sensors for the Raspberry Pi. This here is our BME 680. The one in this work is actually not this the serial connector module. For this visualization, it still works the same, but it will look a little bit different in just a moment. This right here is the actual wiring, so you can see the ribbon cable. This is all very similar to what we just saw. Logic level converters, MCP, and then the power, or the MCP 3008 and our power supply. Here's our sensors. This is actually the bottom side of the lid of our gas cell. You can see the BME 680 there on the bottom, again, slightly different. And then each one of our MOS MQ series sensors there on the top. This is here as it sits in our fume hood. You can see here we also have a watch glass in the bottom of this gas cell to prevent any adverse reactions with anything that may be in there, and also allow for ease of cleaning. So getting into our experiments, we're going to talk about our selected MOS sensors, the target chemicals, some experimental design, a few images, and also a visualization of our sensor response. So our MQ series sensors that we selected is MQ2 through MQ9 for a total of 8 different sensors. You can see there's a little bit of crossover between each of these sensors. They're a bit, they are still differentially reactive, but they all have a different range that they are sensitive to. And these right here is for the chemist, the structure of the target chemicals. So we have ethanol, acetone, and cyclohexane. These are each different classes of chemicals. So and again, here inside the fume hood, we'll talk about, we have 42 different chemical trials, and they were all balanced, so 14 of each chemical, and we'll discuss that more in just a moment. But again, 3 target chemicals. We have ethanol, which is an alcohol. This is also a glass cleaner and laundry detergent. Acetone, a ketone. Nail polish remover, furniture polish, or wallpaper application. And cyclohexane, which is a hydrocarbon, is a solvent and a precursor to nylon. These are all selected due to availability in our chemistry labs, and each one of these is different structures again. Signal collection was installed on a Raspberry Pi. We'll discuss that in just a moment, but it captured values every 30 seconds. Each reading contained a timestamp, the 8 readings from our MQ sensor, as well as the temperature, humidity, the gas ohms, and pressure from our BME 680 environmental sensor. Next, there we go. The gas array is set up inside the fume hood inside the chemistry lab. We had a custom container outfitted with our array, which had a small port cut, which you may have seen that little hole when I showed the lid a moment ago, to allow for the depositing of our chemical using a dropper. And there's a watch glass in the bottom of this chamber again. So sensors must be preheated before experiments. All these sensors require a burn-in time of approximately 48 hours on the initial use. And then after that, any time that you would cycle off a sensor or power down your sensor, you need to make sure that you get back to a baseline. It takes approximately 30 minutes to reach your baseline reading, where your clean air is stable reading. Trials in this work consisted of 0.05 milliliter drops, the approximate value of a single fluid drop. Chemicals may take over 6 hours to completely diffuse, and for the signal to return to baseline. We're not using any sort of breath modulation or air circulation. We're allowing them to completely diffuse. This gas cell is not airtight. Again, it's not sealed, and there is a port cut in it. We do have it inside of a fume hood, and that's primarily to make sure that we don't have any interactions with anything that goes on outside or in that classroom, or any chemicals that may exist elsewhere. And trials are generally conducted once a day, just to make sure there's no accumulation or cumulative, like chemical response inside of our sensors. So this fume hood is closed. We're not dealing with anything toxic or detrimental to human health. So it's closed primarily to make sure that it's isolated. We don't have any adverse interactions. At the time of all these experiments, there's no students having class. We do have some of the solar work going on, which we'll discuss later, going on in this room, but shouldn't affect these experiments at all. This right here is an image of me depositing acetone inside the watch glass, and you can see this red light here indicates that our sensors are on and powered on. This right here is a visualization of our sensor response with clean air. This is over 1 hour. This is how all of the sensors, the baseline that they maintain when there's no chemicals present. And then I'll show you, these are a few of our visualizations of our target chemicals. So this is acetone here. You can see all the 8 readings of our MQ series sensors. Just for sake of mentioning it, the BME 680 sensors, their readings aren't on this scale because they're generally much higher. You have humidity, which is a percentage, temperature, again, Celsius and stuff like that. So to squash everything, that's the only reason they're not in these graphs. But this is acetone. And we have cyclohexane here, and the scale does remain the same across all these, and ethanol. This right here, showing them all on top of each other. You can see that there is a little bit of a difference in the responses here that obviously humans can visualize. But again, the question is, can we use this data for machine learning to predict the chemical labels? So, and I'll discuss this in just a moment. These signals have to be converted into a feature space that we can use for the machine learning algorithms, which we'll discuss when I talk about the event detection Python script that was written. And you can see here at the bottom, which I believe is the next slide. Yes, here we are. So acetone, and we take 25 readings for this specific example. And this is how we melted the data, which again, I'll discuss in just a moment, where we lay each one of these readings end to end for comparison with the machine learning. Each one of these, when we melt it down, becomes its own column with an identifier that we use in to create the feature space for our machine learning algorithms. So getting into data processing, there are a few softwares that were developed for this work specifically. It was originally written outside of the signal collection. Python script was originally written in R and then converted to Python. primarily just through ease of use and allowing to share with other students. So briefly to introduce these, we have a signal collection script, which is continuously 24/7 collecting data from the sensors attached to the Raspberry Pi every 30 seconds. We have an event detection Python script, which detects the chemical events from data that is created by the signal collection Python script. So there's a CSV file outputted that we then process and look through for our events. And then genetic mutation, which is a way of mutating our variables for event detection, the search for better accuracy of the variables discussed in event detection. That might be a bit confusing, but I'll discuss in just a moment. And then a machine learning script, which is how we would split our data and then apply our machine learning algorithms or with the output from our event detection script. So our signal collection, excuse me, signal collection, again, collects signals from the MOS sensors in the VMA680. This continues indefinitely. It can be configured to upload to Google Sheets, but it also does maintain a local copy of the CSV in case there's any sort of connection issue. But there's always going to be the local backup, but this does allow for upload to Google Sheets so you can see real-time changes in your signals. Again, every 30 seconds with our MQ sensors and our BME680 as well as a timestamp. This is a flow chart just to help people understand a little bit of how the Python script looks. Obviously at the top, we initialize libraries. We have to set our addresses for each of our sensors. And then we loop through capturing the readings from the sensors. We write to the CSV, write to the Google Sheets, and then do that every 30 seconds. Continuously, nonstop, 24/7 until a user or some sort of other failure changes that. Event detection, excuse me, is a Python script that was developed to search through the time series data that is produced by the signal collection and detect chemical events. This identifies the events by comparing them to a manual experimental log of recorded chemical deposits. And our output data from this can be used with the machine learning algorithms to predict the labels of these chemical events. So again, another flow chart. We have a couple tuning variables, which we'll discuss in just a moment, which is how we are able to fine tune or make sure that we can change the sensitivity of this, script. And then we process the data a little bit, but excuse me. At the top, we select a specific sensor, which we will then normalize that column and use as our trigger to determine the chemical event. So each one of our events is actually captured by analyzing from the signals from one of our one of our MOS sensors. Excuse me. Again, we normalize that. We determine the occurrence of events using the variables, which we'll discuss in just a moment. We store these events to the data frame, and then we'll melt them like I discussed earlier, where we take them from wide form data into a single column, transpose that into a row, and create our feature space for our machine learning. We also store some parameters such as excuse me, the total number of events that were desired, as well as the amount that was actually collected, so you can fine tune your parameters, which the genetic mutation actually attempts to do. So variables used to determine events, we have srun, future, average, and expected change. So srun is an integer as well as future average, which is the number of values averaged before our current index. The future average is the number of values averaged after the current index, inclusive of the actual index. So as an example, if we were on index 5 and we had an srun of 2, we would then look at 3 and 4 and average those together. And then if we had future average of 2, you would take 5, 6, and 7, excuse me, and average those together. And then our expected change is our threshold, which is a decimal value. When our average values, when the difference is taken, exceeds the expected change, we'll determine an event. We also have window size, which is how we determine our length of events. And we use this primarily for comparison with our machine learning. We'll discuss that in just a moment. But the different lengths that we're using all have the pre-window of 5. So that'd be 4 values and the index itself. And then everything beyond that would, if we have like an example, we'd have 25, we'd have 4 before the index itself and then 20 remaining. So event detection, again, selects a target sensor, uses these two variables. The past and future averages are calculated. The difference between these means is then taken, and then when this exceeds our threshold, we determine that as an event. Then from there, excuse me, one sec, I'm sorry. Upon occurrence of event, we have window size, which will determine the length of events stored. So we ran this several different times to capture different lengths of events. The data structure here, when we melt them down, again, as we saw earlier, we lay them end to end, making them long, or versus the wide form readings, it'll just be a single row. And each one of these will contain a suffix, excuse me, indicating where in time this reading takes place. So for example, here, as it shows, MQ2 ADC1 would be the same as MQ3 ADC1, as well as 25 to 25. So each one of those will represent where it occurred in the event. And this output is used for machine learning. With this specific script and the way it was configured, with the srun of 3 and future average of 1, I want to be specific with that, with the way the indexing works here. Of 1, that would include the index itself as well as another value, so it's a total of 2. But with these variables, we had 100% accuracy, meaning that all of our different chemical trials were detected and identified successfully with the labels from our manual experimental log, with no false positives, so we didn't have to cut out any quote unquote noise, excuse me. So genetic mutation iteratively fine-tunes our parameters and variables of event detection and attempts to minimize our manual evaluation of these variables. So it produces scores of fitness and utilizes bit flipping. So it creates a dictionary of bits, zeros and ones, and this dictionary is used to calculate our values of our variables. So real quick to go through this flow chart, obviously libraries in your data set, we load, then a random bit dictionary is created. We set variables for search range. A user can set the range for what you want to search in. Then each time, each iteration, the bit dictionary is used to calculate the variable values. We then, perform the event detection Python script with these new values, calculate the scores and compare the scores, and then we store the best score. And after 18 iterations of this, which is 18 bits is what is used in this current program, we then will take the best score and use that as our seed for the next iteration of this, where we flip through each bit once again. So again, this is designed to tune itself to finding true positive chemical events while punishing itself for false positives, minimizes the user manual evaluation, but does require a lot of computational time, and it skews for lower values to make this less sensitive. And again, the range of values can be set by the user. Excuse me once again, I apologize. Again, you initialize the dictionary bits, calculate target variables, and here specifically, the first 10 bits are what it changes our expected change into float, and then the final 8, obviously the first 4 of that is for srun, the final 4 is for future average. Each time you do this, you produce you calculate your value, use that as your variable, and perform the whole script once again. Best scores are stored, and we produce the CSV that it doesn't produce the events, but it produces a parameter list that can be used to find whatever the best score was, and shows those parameters for what you can use for event detection to actually store your events from there. So machine learning is a pretty simple program that applies the machine learning algorithms to the event data that was produced by event detection. It creates our train and test splits and outputs scoring, which we'll actually use in our results. So, I'm sorry. We initialize libraries, load data sets. We select different algorithms. So each time you run this, you can the user can select an algorithm. We create indices with a module we'll describe in just a sec. We have a train and test split. We train the model, test the model, output the results, and we do that 10 times. And we average those 10 together for the final results that we'll show later. So stratified shuffle split is a method we use to cross-validate, excuse me, and to determine our train and test set. Creates indices or indexes, rather, I believe it's indices, excuse me. All classes are balanced. Like I said before, we have each one of our target chemicals is balanced and produces a single train and test split, but we use in splits argument to determine the number of indexes that are then created. We introduce, excuse me, I'm going to introduce supervised machine learning module, excuse me. For this next section, I'm going to introduce the supervised machine learning modules that we use, scoring, and then a comparison of our results. So all modules discussed here, including stratified shuffle split, are from the scikit-learn library. I may also refer to it as sklearn. But we have the Gaussian naive Bayes, k-nearest neighbor, support vector machine, and random forest. These are all supervised machine learning modules where we use a train and test split. So to begin discussing Gaussian naive Bayes, based on the Bayes theorem used to calculate conditional probabilities. This Gaussian variant is capable of using continuous values, and it assumes these classes are all normally distributed. Specifically, the Gaussian naive Bayes also assumes that these values are independent. Each feature value is independent of each other, but assuming that from each reading to the next would be completely independent. Despite this, Gaussian naive Bayes still seems to have relatively good success when dealing with problems like this. Gaussian naive Bayes is also useful for small data sets, but this implementation here has no parameters to tune. K-nearest neighbor, the output of this is a class membership where objects are classified based on a vote of neighbors, and distance is measured from the pre-classified data or the training data. And then the K, which is one of our parameters that we tune, you get the vote of the K of your nearest neighbors, and the class that appears the most between those votes is the correct classification. In this work, our K is 5. Support vector machine separates points using a hyperplane or decision plane. The hyperplane is generated iteratively, and support vectors are our points closest to this hyperplane that is used to define the separating line between our classes. The goal is to find the maximum marginal hyperplane to divide each class. And this is generally considered much more accurate and faster than naive Bayes, but takes more computational training time. And just to mention here, there's not been an issue with computational time in this specific work. So this right here is a visualization of a simple visualization of an SVM. So you have your classes here, and then your hyperplane would divide each one of your classes. And then obviously the ones that they're not marked here, but the ones that are closest as hyperplane are your support vectors. In this work, we use a linear kernel, which is the most common variant. And this is chosen when a data set has a high number of features. Like in this work, it could be upwards of 300 pretty easily, depending on the window size and depending on the amount of sensors that are even used as well. It's usually the fastest, but when data can be separated with a single line, which may not be the case with a multi-class problem like this. Random forest is based on decision tree. It actually uses multiple decision trees for voting. Combats overfitting and also, again, fits a number of decision trees to subsamples of our data set. So our data set is divided into different feature sets with each of our decision trees voting on with the most important features. It averages the predictions, and then specifically about decision trees, each node of a tree is a test against an outcome with branches representing that outcome, with leaves representing the class label. And this next one, this is kind of a visualization of a single decision tree. And you can see at the bottom where the classes here with cyclohexane, acetone, and ethanol, these are our leaves of the decision tree. random forest, again, using multiple of our decision trees. The arguments that can be used for tuning in estimators is the number of trees built before our prediction. More trees, better performance, but more computation time. The depth is, or the max depth, excuse me, is the max depth of the tree. And the criterion is used to measure the quality of splitting. You have G and I impurity and entropy. And for this work, number of estimators, we use 100 different decision trees, and max depth is set to none. So all nodes must be pure. Again, we're using entropy in this work, focuses on information gain and indicates disorder. In contrast to our GINI, not sure how to say that, impurity, which measures the frequency at which elements are mislabeled when labeled completely randomly. Entropy is computationally heavy, but generally considered much more accurate. Again, stratified shuffle split, used to split our data. We use a total of 10. The results of each classifier is average, so our results that I'll show in just a moment are all averaged between these 10 splits. We have a training set of 50% as well as a test set of 50%, so split right down the middle. There are 42 trials across our 3 different classes. And I want to make sure that I mention that classes here is machine learning classes. We're not balancing, or we're not trying to identify the class of a chemical. We're trying to predict the chemical label. So again, balanced across those 3 classes with 14 trials each. And then a window size of 25, 50, and 100. And again, that window size is after the event has been determined, how long we continue to record and then store that event and use that for our machine learning comparison. So part of our scoring that we'll see in just a moment, we have accuracy, which is a representation of all examples that are correctly classified. Precision is the proportion of predicted positives that are correctly classified. And recall is the proportion of all positives that are correctly classified. Precision and recall are macro averaged here in the results, as it's a multi-class problem. If you're familiar with binary classification, the macro averaging will take each one of our classes and set it as a binary classification problem and average those all together. Precision and recall may struggle or not, it may not struggle, may not be completely indicative of performance in this specific use because we have completely balanced classes. And so accuracy, precision, and recall sometimes will appear to be the same. And the reason why in our results in a moment it'll be a little bit different is because of this macro averaging. This is a confusion matrix for a typical binary classification problem. So you have your predicted labels and your actual labels. And if you predict an actual, so a positive or negative could be an either or type problem, cat or dog, things like that. So if it's predicted as a dog and is a dog, then that's a true positive. And if it's predicted as a dog, but it's a cat, that could be a false positive or a false negative, depending on your classification and how you look at it. So I'll show here the, this right here specifically is a confusion matrix for our Gaussian naive Bayes with a window size of 3. So our n number of classes is 3 here. You can see these dark blue, the dark blue cells are actually our correct classification. That would represent our accuracy. And you see on the side here where we had a cyclohexane, 2 of our trials were actually incorrectly predicted as acetone. This right here is my the classification results. You can see on the left are each of our learners. So G and B, Gaussian naive Bayes, KNS, K-nearest neighbor, random forest, and the support vector machine. Again, recall and precision are generally really close to accuracy. In just a moment on the next slide, I'll cut this out and it'll cut down a little bit on what we need to look at. But you can see here, random forest at window size of 25 had 100% classification across all 10 of our splits. Each one of these scores is an average of our 10 splits. So, excuse me. So here again, looking at just accuracy, these results, these results show that successful prediction of chemical labels using this method is possible. Random forests achieve the highest accuracy at 25 window size, but seem to struggle with dimensionality. Random Forest actually does a good job of combating dimensionality because of the way it segments our data. I believe this to be due with our decrease in performance here. I believe this has to do more so with the way our response curve from our sensors affects, because once you run up to the top, it's a slow taper down over many hours. Our Gaussian naive base performed the worst. Excuse me the typo here, but performance increased actually with the number of windows. And I believe this has to do with the assumption of independence between each individual feature, while KNN and SVM both had a flatter performance curve. And I want to get more into a little bit about the future of this work and talk about SolarRid. You can see here on the left, we have one of SolarRid's smart bug zappers, and also on the top, you can just barely see one of our gas cells. So the theory is that utilizing VOC analysis, that it may be possible to identify specific species of insects, and maybe even more specifically different life stages or various different, possibly like brooding season and such like that. Excuse me, I'm not an entomologist. But you can see here we're doing a chemical trial in the base of this glove box to make sure that we can measure the VOCs still. And on the right, here's me handling some moth larvae. So again, the theory is it possible to analyze VOCs and identify specific insects? Currently, the only insects being tested are moths. And you can see here again the gas array on the top, and on the right here is a moth that has been successfully killed on the grid. And this next one right here, you can actually see on the image on the left, and I hope everyone can see it clearly, is one of the moths being actively fried, if you will. And on the bottom right is our same gas cell responding to our excuse me, responding to the emissions of that moth as it gets fried. And this is more work that's being done currently. You can see Elena, one of our other graduate students, installing, I believe it's an LED matrix, as well as over here on the right, one of excuse me, one of the bug zappers actually being used in the field. Currently, this doesn't have our gas array connected to it, but as the work is ongoing, that'll change, obviously. And yeah, this is my email address here. I appreciate everyone joining me. Yeah, any questions?
Yes, thank you, Hunter.
Thank you.
Perfect timing, 10:46, excuse me, 2:46.
Yeah.
The members of the committee will hold off until after guests have had a chance to ask questions. So if you would like to ask a question, it would be nice if you could turn your camera on and please ask Hunter some questions. And turn your microphone on.
Please.
On slide 50, did we see some saturation of signal?
Yes, and oh, shoot. Give me one sec, I apologize. Let me stop my share real quick. So the saturation of signal, yes, there was some of our chemicals will reach a value of 1 on our sensing elements. Give me one moment, I apologize. That was not supposed to happen.
You trying to share your screen?
No, it logged me out of my my UALR email, so I'm getting right back in. I just had to authenticate with the password manager. So give me 1 second as I get everything back going. I am now on my presentation. Give me 1 moment. I apologize. Here we are. Can everyone see?
And please, if you're not on the committee, please ask a question now. If not, committee members will.
All right, so I apologize, Dr. Wim. You said 50, I believe it's this slide, correct?
Sure, that'll work.
Okay. So yes, there is a bit of saturation on these. You can see on ethanol and acetone both. Acetone typically would reach the top of this graph. We did attempt to, or I rather attempted to mitigate this by going down as small as I could with the drops. There is a point, again, because at 0.05 milliliters of each chemical, that it's more difficult to mitigate that with the instruments that were used. But this does reach saturation for a moment. So you can see acetone and ethanol both reached a value of 1 and stayed there for a minute or two, approximately. Despite this, we were still able to have successful classification.
Hunter, why don't you explain what saturation is to members of the audience who may not know?
Okay, so again to the MOS sensors, because of the oxide, the oxide and how it interacts with oxygen and our chemicals, complete saturation here would more so mean that the reducing gas is blocking all oxygen to our sensing element, increasing electron flow to the maximum. And then as this diffuses and oxygen is able to be reintroduced and bind with the sensing element, we decrease our signal as electron flow is slowed due to the oxygen. I hope I answered that sufficiently.
Not from the perspective of a chemist, but how about answer it from the perspective of your graphs and the features of your graph?
I'm sorry?
Can you answer the question just from the perspective of the graph?
Oh, so full saturation would be a value of 1. Is that how you mean?
Right, so we have no idea what the true value is.
Yes. So in regards to that, excuse me. So to be more clear, these values are all raw values from our sensor. They run at 5 volts, but the way that this is taken in is again more of a scale of the signal. You can take these values and perform it's a pretty simple equation to get the true voltage readings of these compared to the 5 volt. But this is more so, again, just the raw voltage with no processing outside of just setting your addresses of your sensors and taking that into the Raspberry Pi. So your 1 would be a maximum of 5 volts, and everything else is a scale between that.
Does anyone else have any questions? Okay, if no one has any questions, then maybe we should ask everyone to leave except the members of the committee. Phil, do you have a question? You're muted.
I got it. Technology. I'd like to thank Hunter for the work he's done. I can see for the first time how this is going to fit into the things we're going to continue to do. And it appears to me, at least, to be a foundation for the things that are going to follow. So on behalf of us, SolarEd, thank you and good luck with your endeavors.
Thank you, Phil. I appreciate it.
As you move forward.
Thank you so much. I appreciate your support.
Okay, thank you, Phil. All right, then I think I would like to ask everyone to remove themselves unless they have a question, and the committee will ask our questions.
Okay, so
Okay, who is John?
yeah, who's John?
Maybe my grandfather.
Okay,
It may be.
you want me to hang up and and then we just resubscribe?
That works for me if that's what you'd like to. That's no problem.
And simply kick him out, no?
Yeah, I think the host could, disconnect.
Okay, let me hit more participants. John, remove.
That
Remove
was
John.
easy.
Submit. Who do you want to remove? Submit. No?
Looks like it. I think we're good.
Okay.
Okay, already done. Should I start? I
Sure.
start. I was actually impressed after the first drafts I saw. So that feels more like a thesis than many other things I see. There are lots of bumps in there, I think. I haven't, from my point of view, obvious technical question, and actually the slide you brought up is the right one. You're talking about basically melting the examples or basically creating features
Yes.
and making this through Windows. And it sounded like a little bit like there was an intuitive gut feeling like process. It probably wasn't like that. But my question is there a more formal way to do things like that? Do you know? Did anybody
Of
tell
doing
you?
melt.
No, to basically do this kind of signal analysis.
Mm-hmm.
Do you know?
You're talking about in regards to eNoses and like the signal analysis of these MOS sensors.
Mm-hmm.
So yeah, there's a few obviously more industrial uses of eNoses that do utilize.
No. In general, in a more mathematics-based way, how could you do this in a more formal way to figure out what's important here and what is not?
Oh, so one way that, if I understand correctly, when you're talking, I guess are you talking about in more so like selecting the different MQ sensors?
Or are you talking about detecting an event?
Well, it's basically both. Okay, so you probably don't, else you would already have said Fourier analysis, you know? This is what Fourier analysis is for. Or you could also use wavelets, okay, to basically figure out what is going on. And actually the nice thing about that is it's basically doing a transformation in a different space where you don't have to actually look at the time component, not in the way it's basically going around here. So for me, that would have been obvious thing to mention at some point, even if you don't use this, because I mean, let's be honest, sometimes it's a little bit hard to do. Or actually, I think there is probably work around already that basically takes the raw signals and does as a preprocessing pass in your machine learning, basically the appropriate stuff to basically get signals, or basically the signal and the detect into the remaining of the machine learning evaluation. Okay. The other thing that is just a slight comment, I would actually have liked that half of the diagrams you show in your slides ended up in the thesis as well, because, you know, that would have made things much more easier to understand.
Okay.
Let's put it this way. Yeah.
Okay.
That's from my side. I
appreciate that feedback, and I agree. I think there's definitely more stuff to include here. So I appreciate that.
I'm good.
Bill?
Hey, Dr. Springer.
Good work. So a lot going on there, and I like the look to the future as well.
Thank you.
Mary?
Nice work. So I think I do not have any additional questions.
I appreciate it. Thank you, Dr. Yang.
Well, Hunter's been getting my questions ferociously over the last 2 weeks. I don't think I have any either. I mean, we've been talking about this on a daily basis. Jan, one thing we wanted to do with the voltage discharge was to try and do Laplace transforms on that. Another student, Haras, was going to start tackling that. But Hunter's work, you know, that wasn't Hunter's work.
Yeah.
No, I appreciate the feedback, though. I think it's a good way to frame things, though.
Yeah. Well, it's basically the standard way to do, because it's well, I don't know why it's called a capstone project. This is a master's thesis, you know. You took something that is it's not unknown, but you put it back together in a way that shows mastery over the skill set in a bachelor. So that's pretty fine. And then usually it's necessary, and you try to do this in the beginning with a literature review to also basically look what kind of methods you have to do, this kinds of things, because you already know what the end product is because you did it already. So you can actually write the whole thing by knowing, okay, I can prepare this and I can prepare that, and later on I can pull that out and can say, no, we don't do this because A or B or whatever, you know. So you don't have to write this in the terms, and then I did X, and then I did Y, and then I did X again. This is not necessary. You can split it up by aspect instead of over time. And that's much more like scientific writing than anything else, which it should be because it's a master's of science. Okay, good. What's the formal process right now? We got to sign something, or how does it work?
I think if I understand right, what I'd like is, Hunter, why don't you hang up and I'll send Vincent or Tommy down to your office because he's just down the hall from me.
And you can email me or whatever.
I'll just send him down and give us a couple of minutes to chat, and then we'll ask you to come back.
Okay, we'll do.